期末考对啊，以现在疫情来讲，我们还是线上考吧。但是可能等一下再宣导一次吧。就是期末考，因为期中考有些同学有点踩线的行为，希望你们期末考的时候不要出现不要出现看起来像是讲话的样子。你们应该是写考卷，应该是不需要讲话的。对，所以期末考这些比较脱序的行为，请不要再做。期中考是我们那个情况有点混乱，有脱序行为的话，我们可能需要考虑以作弊来处理。这个我们两边都很不方便，所以请不要有。Okay, it's time. Yeah. So first, people were asking about finals. So finals, we are going to take online exam, just like midterm. But there is something additional I want to say. So please don't cheat on your finals. And also, there were people that are doing very suspicious behavior, like they were talking in the midterm. So yeah, I don't think you need to be talking while taking an exam. So please don't do any talking at the finals, otherwise they will treat you as you are cheating. So yeah, that's that. And for headphone, I'm not sure how much you guys actually need headphone. But I guess that's okay. So yeah, I will. That's a little tricky. Let me think about it. Is there a reason why you guys need to put on headphone during exam? Because I see quite a bit of you put on headphone where you were taking meter. But no response. Yeah, I guess I was thinking about it. But yeah, but talking is banned. No talking. Your mouse should not be moving where you take the exam. Okay. So yeah, final is going to be similar to the midterm. You take online and we turn on camera and we'll show your face. Okay. Okay. Then let's have this final teaching of new materials before the end of class. Okay, so let's go back to our Laplace Transform and all those post-zero analysis. So this time we were talking about this spectral factorization stuff. So we're talking about opaque system and the minimal phase system. So opaque system was a system where the point zero structure is asymmetry. So when you look at the Laplace look at the Fourier transform on the geometric axis, the magnitude is always constant. And so that's cool. And for minimal phase system is a system where all there is zero in the poles on the left hand side. So when you do an inverse, then you revert to the point zeros, and they are still going to be a left hand side. So the inverse is also causal and stable. So that's also pretty cool. And we have this some kind of factorization where if you're seeing your pole zero are not all on the left hand side, then you can decompose them. You can kind of move the right hand side zero and move this right hand side zero to left hand side zero and by composing another open system. That's pretty cool. And I guess it's a question from last time. If not, then let's talk about this virtual factorization. So this is similar to what we do at the buttonwood filter. So we are given the information h of j omega, or sorry, let me. Yeah. So we are given information of the absolute value of h of j omega or h of s. So it's something that's given, and we want to construct some h of s that will have this absolute value. And so we start with decomposing this absolute value into real part times imaginary part. Then we want the construction to have a real impulse response. So now we know this complex. So something that is complex conjugate. So we know the complex conjugate will be just getting a negative sign in omega, and then we try to satisfy this by having the left hand side just equal to h of s equal to h of s times h of minus s. So we have this, then when you restrict s to j omega, obviously it's equal to that. And but this is quite a restrictive form because if you think about this thing, then h of s, whenever h of s has a pole at a, and h of minus s will have a pole at minus a, and so these terms will be all factors looking like minus a squared plus a squared, and so it's not necessary that you can always find your thing in this factorization. But lots of time you do, and we'll have an example that we do. And if we do, and we'll get a spatial factorization. So let's talk a little more about this h of s times h of minus s. And so really, when you have a pole at somewhere, you will get our four poles. So first we say that is h of s times the minus s. So if you have a pole at s, you will have a pole at minus s. And also we want our small h to be real, so we also have this up-down symmetry. So when at the complex conjugate rotation, we'll also have a pole. So actually you get a complex conjugate, so from here to here, here to here, so you got two poles here. So really one pole, you got four poles. And so that's the poles of h of s and h of minus s. And hopefully the thing given here will have those pole structure. And yeah, but then you got those poles, and now you want to determine h of s, just h of s by itself. Then what we do is now we need to assign the poles to either h of s or h of minus s, and then we know that it comes in pairs. But anyway, we usually want our system h of s to be stable in the causal. And as you say, that means all the poles of it should be on the left hand side. And because this h of s and h of minus s, the poles of them are in pairs. So whenever h of s take a pole on left hand side, and h of minus s will have a pole on right hand side. And also if h of minus s has a pole on left hand side, h of s will have a pole on right hand side. So yeah, this left hand, right hand, they are in pairs, and you want so each pair you need to decide whether they belong to h of s or h of minus s. But obviously, if you want system to be stable in the causal, then you want all the left ones belong to h, and all the right hand pole belong to h of minus s. So that's that. but so you can determine where all the poles are, and but this thing also has zeros, and we don't actually have any constraint on zeros. So zeros are also going to be in those pairs, and you can assign the zeros to h of s or h of minus s. And that's actually kind of arbitrary. There are many constructions that are good spectral factorization for h of j omega. That's just because h of j omega don't tell you all the information about h of s. Okay, and that's the very well constructed example. So we have h of j omega equal to this nice rational function omega squared and omega 4 or something. And when you factorize it, it's omega squared plus 1, omega squared plus 4, omega squared plus 9. And so you can write down the pole 0 plot. So 0 is plus minus 1, and poles is plus minus 2, and poles is plus minus 3. So it's actually even easier than this thing. This thing, we say you have a pole, and you get 4 poles, but everything is on real line here. So actually, one pole is just a 1-1 pair because you don't need to go up down. There are no up down symmetry getting you extra poles. But we can still assign the point zeros to h of s and h of minus s. We think this thing is equal to h of s and h of minus s. Oh, sorry, we are skipping a little too much. So this is talking about omega. But we have s equal to omega, so omega squared equals minus a squared. So it's actually equal to, so in terms of s, it's actually this. And but anyway, so you solve for the positive, so for all the positive zeros, and you see that in pairs. That's really nice. We are given a nice function to start with. And as we say, so all the poles on the left hand side should belong to h of s. So h of s should have this s plus 1 and s plus 3 here. But the zeros can be assigned either way. You can either have h of s take this pole 0, or h of s taking this 0. So h of s actually has two choices here. You can have s plus 1 up here, or minus s plus 1 up here. Both of them will give you the same product of h of s, h of minus of s. And so if you have extra information, then you can probably determine which one is true, but we're not given, so either of these is a valid spatial factorization here. Okay, so any question about spatial factorization? If not, then let's go to the other topic. So this is kind of an engineering topic. That is, we want to draw block diagram to represent some system we want to build. Maybe some differential equation, and we want the input output to satisfy, and they want to draw block diagram. And then if you are an electrical engineer, then you can probably build a system or a circuit or something that satisfy the block diagram, and got a good system component to whatever electrical system you want to build. Maybe a filter or something. Okay. And so now we start with I think it's a review of a very basic about the bar diagram of a system. So an easy way to compose different systems is two easy ways to compose systems are this parallel interconnection or this serial interconnection. So parallel interconnection, you will split your signal into two identical signals, feed them into two systems, and then combine them together and output somewhat. And serial, you put your signal through one system, then put this output through another system and get your output. And so we will be a little confusing about notation here. So the system here we are assuming LTI, so they can be represented either by the impulse response or the system function. And so But sometimes we use impulse response, sometimes we use system function. I guess you need to look at a variable here. If it's a function of s, then we are talking about system function. If it's a function of t, then we are talking about impulse response. Anyway, that's that. And then, so the last time we talked about this was in chapter 2, and we only know impulse response. But now we know a little more, so we can know about how system function work when you compose your system either in this parallel way or serial way. So in parallel way, we'll know nothing too much happen. So this parallel system is effectively just adding the two systems together. If we have the impulse response of the whole system, it's H1 plus H2. And then you do Laplace transform, it's linearity, so big H is also big H1 plus big H2. And the serial interconnection is a little more interesting. So if you remember what happened, it is, so we have like the convolution is going to be associative and commutative sort of thing, but anyway, the effective impulse response will be the H1 convolute with H2, and now you take the Laplace transform, and you use the convolution property, you see that the effective system function of this thing is big H1 times big H2. So that should be pretty clear. Any question? No. Okay. And okay, then now we start to build something really interesting. So we use this, and okay, let's go a little slower because it's going to be the building block of probably this section for probably the next 30 minutes. Okay, so now we can use this feedback system to build something very interesting. So what does feedback system do? So we have some signal input and go through one system and the output, but we also have a feedback. So on the output here, we do a split copy and the feedback through another system H2, then adding together to the input. Okay. So this is a feedback system, and we want to solve for, so what's the effective edge of this whole feedback thing? So the relationship between x and y. And okay, and then yeah, we go to the S domain to analyze everything because that's easier. So in the S domain, and so we basically go through every weird part. So all the line here, all the line splitting here, they're actually all equal to y. So it's also y here. So the first part, the first equation we are looking at is H1, and so E will become y. So big Y should equal to H1 times E. And for the second equation, we are looking at this addition operation here. So E should equal to, and we give whatever here name Z. So the signal here is Z of t, and the Laplace transform is big Z of s. And we see that, oh, and we actually also get a small minus sign here. So those are not quite addition. It's okay. But anyway, so it's actually subtraction here. So E is x minus, so small e is small x minus small z, and you do Laplace transform, and big E equals to big x minus big z. And then down here at this H2, so similar to upper layer. So these lines, this is y, and this is y, and this is also y. So this thing, what happened here is y turn into z by H2. So z equal to H2 times y. So we have those three equations. Any question about bilateral? So the three equations, what happening is this feedback interconnection. Okay. And well, now we want to solve for what's y in terms of x. and we'll well, you do some algebra to eliminate all the E and Z. Basically, substitute the E from here, then substitute the E from here, and you get this relationship. So y equal to h1x minus h2y. And then you move things a little around more, so you're grouping all the things with y together and all the things with x together. And you can get our system function, which is big Y divided by big X. And yeah, and the coefficient on X will be H1, coefficient on Y will be 1 plus H1 times H2. And so that's what we got. Any questions so far? Okay. So yeah, we can build something interesting by this feedback loop. So, and basically, what we get is the ability to get this something over something. And okay, then then a good application of this is when we put H1 as an integrator. Okay, so remember integrator has its impulse response being equal to h of t. And if you do Laplace transform of this thing, then its system function is 1 over s. So if we have integrator here and a minus 3 here, which is equal to a plus 3 here and a minus sign here, you're just moving the minus sign around. Those two are the same. But anyway, if you have this thing, then we plug in the previous formula this. So now h1 equal to 1 over s and h2 equal to 3. Then 1 over s, 1 over s is 3. And you can multiply this up and down. Then you get 1 over s plus 3. Okay. And this is a really nice Laplace transform, right? This is the example we keep talking about. The h over t is going to be exponential decay with a rate of 3. And if you write this as the differential equation, then that's dy dt plus 3y. So this s becomes dt and 3 becomes 3 and equal to x of t. So we see that we can, if we build all this feedback interconnection, then we can get first order differential equation like this here. A system that's represented by this first order differential equation. Question? And yeah, that's pretty cool. And basically the elements we use here are just splitting and header, integrator, and this is, I think it should be called amplifier. You are just multiplying by a constant. Okay. And okay, so obviously, then you can build all sorts of first order differential equation just by something like this and tuning the coefficient here, then you'll get a different coefficient. But what if we want to build something weirder? If we want, well, it's still a rational function, but what if we have something on the upper side? So we have s plus 2 over s plus 3. So how do you build this from blocks? Well, a very stupid way to build this, or I guess a very intuitive way to build this, is you just write this s plus 2 over s plus 3 as 1 over s plus 3 times s plus 2. Then you remember that at the beginning of this section, we say if we have a serial interconnection, then the big H, then the big H will be multiplying together, right? So reminder, here, yeah. So this thing, if we have a serial connection, the H will multiply together. So we can just have our feedback loop here to give you 1 over s plus 3, and another thing that give you s plus 2 here. Okay. So yeah, so the zero thing, we kind of think x getting to z, and z will be 1 over s plus 3 times s, and then big Y will equal to s plus 2 times z. So we can build this way, but that's a little annoying because if you think about how to build this thing, so this S is actually how to build because you want to have a system that turns y equal to s plus 2z, then have y equal to dz dt plus 2z. Yeah, you just do the inverse Laplace transform, and this s will come from differential property of the Laplace transform. But as we keep saying, we like integrator, but we don't like differentiator because differentiator are hard to build and not very stable. Yeah. So that's annoying. But there's a way to. That's annoying because we don't want to build a differentiator to get this SD here. But then we notice that we don't really need to do differentiation here because we already do an integration here. So if we skip this integration, then we already have the differentiated result, right? Because differentiation is the inverse of integration. So if you just don't do integration, then we already have the differentiated result. And I will see this is you have a times s here, but you are multiplying one race. So if you just take something that haven't been multiplied by this one race, then that's equal to this times s part. Okay, and yeah, so that's what we do. So we notice this dz dt here is equal to this e of t that just happened before this integrator. So instead of building this thing using differentiator, we can build this thing. So dz dt plus 2dt, we use e of t plus 2dt instead. So we still have this thing, and we take the 2z part from here, and the e of t part from here. We add it together and output. Yeah, and now this thing don't have a differentiator, and we're pretty happy. Any question about how we build this thing? No? Okay. And it's pretty cool. And I guess this is the same thing. Just a review. So we have t, we want to be dz dt plus 2dt. But the dz dt is annoying, so we take, instead of dz dt, we take e of t here. And the two property we use here is that the differential property on time. So when we take a signal and the derivative in time and Laplace transform get h twice, and you do integration and you get a one ways. Okay, then let's get a more complicated example. So before we have one over first order thing. So now we have two poles for a system function. We have 1 over s plus 1 times s plus 2, and it's, well, if you expand it out, it's s squared plus 3s plus 2. And it's representing this differential equation, dy squared, dt squared, and dt squared, and this 3 and this 2, okay? And now we can also realize this in block diagram. And you can see that this is very general. If you have a higher differential, you can do all the similar thing. This example is kind of a rule for arbitrary 1 over polynomial. So yeah, it's here. So this thing will be representing this differential equation, because so first you can move things around here. So you can keep this dy squared dt squared on the left hand side and then move everything to the right hand side, and that's equal to this thing. And if you compare the thing here, so you see that you have two integrator here, and so this is y, and this f will be dy dt, and this e will be df dt, which equal to d squared y dt. And so this is e of t. And we want this e of t to be minus 3 of dy dt, which is f. So yeah, so we do that. So minus 3. And also minus 2 of y of t. So y of t is output and it's split here, and we times the minus 2. So adding together and then add together with x of t become u of t. Okay. So you can see that this thing will satisfy this differential equation. Your dy dt will be your x of t, and with those two feedback is negative 3, negative 2 adding together. Okay. So this is called the direct form block diagram representation of a system. Okay, so it's quite direct. If you have a differentiation, you just do a whole bunch of integrator here, and the lower order terms you can build feedback and then will multiply by whatever coefficient here. Yeah. And so any question how to build this direct form block diagram? Not. So that's a direct form. But for whatever reason, you might want to build other form. So you can also build it as a cascade form. So you build it as 0 of 2 system. So what you do is, instead of thinking h of s as this thing, you think as so you factor the pole into 2 parts. So you think it is 1 raised plus 1 times 1 raised plus 2. And well, you know how to build 1 raised plus 1 is this feedback loop, and 1 raised plus 2 is this feedback loop. So yeah, so basically you are building the second order system as 2 first order system. Okay, and because you know if we put that in serial form, then the system function will just get multiplied. So you get this. Question? And finally, we have parallel form. And what do you do here? Well, we also start with formula. What you do is you do partial fraction expansion on your system. So now this is 1 raised plus 1 minus 1 raised plus 2. And yeah, so you think the system function as a difference of 2 first order system. And once again, you have 1 raised plus 1 here. That can be built by this system, and 1 raised plus 2 can be built by this system, and negative sign just multiply negative sign and adding the two signals together. So that's a parallel form. Question? Okay. So yeah, once again review direct form. It's a line and two feedback. And the parallel cascade form is a 0 of 2 first order system, and the parallel form is the sum of 2 first order system, second order system. And then now let's see this example. No, the example is more complicated because we have this upper side once again. So we have this second order polynomial here and second order polynomial here. And well, we can build a plot diagram for this thing in several ways, just as before. So first is we do this kind of stupid the numerator multiplying the denominator thing. And oh, we don't have a picture of this. And but once again, if you want to build this directly, now this numerator, this is 2x squared plus 4x minus 4 minus 6, is going to give you 2 differentiator here. But you don't like differentiator. Okay? So the lower part, obviously, we already built it, and we can build it in state form, like standard form like this. But the upper part, this 2x squared plus 4x minus 4 part, we don't want to just zero another system with differentiator. So once again, we are taking from the earlier part, and yeah, so just like this, and we skip the analysis, but you can publish it. So you are tapping from here. So this output is going to be like it's a little. I guess we. Okay, it's a little weird, but yeah, I believe it is correct. So the output is kind of like y, and so you go back the differentiator, then sorry, you go back the integrator is like taking differentiation. So instead of putting, what do I say? Instead of oh, okay. Yeah. Instead of putting differentiator on this y, we can just take from before we do integrator, and that will be like doing differentiation. So this 2x squared you can just take from here and then times 2. This 4x you can just take from here times 4, and then you have minus 6 here, and adding them together, then you get a y will actually correspond. So you will get this block representation will actually equal to your h of s here. And I think this should also be called direct form. Yeah, you can think about different form. We'll have an example. Yeah, so that's a direct form to build a system with a rational system function. Okay, but this might be really annoying. If you look at this, it looks very, very annoying. So you can also build in different form. So in particular, you can build like serial form like this. You have 2 serial parts, and yeah. So it's first order over first order here, and first order over first order here. Or you can do just partial fraction expansion and do it in a parallel form. I think this might be simplest if you want to draw it. But yeah, so you can write your h of s in different way, and then you write it with like a product of multiple terms. Then you can build a series of systems together. And if you do partial fraction expansion, then you can build a system of this by doing parallel of several systems. So any question on this building of building block representation of of some system function? No. Okay. So that's quite interesting. And okay, finally, the last topic in our Laplace transform is a different form of Laplace transform called the unilateral Laplace transform. And I guess we are hinting at this multiple times, but but what it's most useful for is it can solve a differential equation with initial value problem. Okay. And yeah, we should have enough time to cover that today, and even some chapter 10. Anyway, let's see how this goes. And yeah, we start with the definition of unilateral Laplace transform. So unilateral means one-sided, and that's because the definition is basically the same, but we are integrating starting at t minus. Okay. So usually for the bilateral Laplace transform, we are integrating from minus infinity to infinity. But now we are going to integrate from infinity, but on the other side, we just chop off at t at 0 minus. So obviously, this thing will not depend on x of t for t less than 0, right? So yeah. But yeah, Okay, so the first thing we should say is what? Sorry, the order is a little. First thing we should say is what is zero minus mean. The zero minus mean means that we are integrating over all the singularity that will happen at zero. So for example, if you have x of t equal to delta of t, then that will give you something that will give you a 1. Because you will integrate over the delta function at t equals 0. And if you have a weirder thing, then we'll even also take that. Maybe you have a u1 or something. Okay, so that's what this notation means. Any question? Not. And yeah. And then we need some notation to differentiate between unilateral Laplace transform and Laplace transform. So we will write the transform pair as this x of t and big X of s. But now this big X, we are using this weird script front. Okay, and we have the UL here for unilateral Laplace transform. Okay, and so there are also going to be inverse, and we'll see the inverse later. But okay, then the point I was making is that since the integration starting at 0 plus, so anything that's less than t on t less than 0 plus doesn't matter. Okay. So I should say intuitively it's because this is basically designed to study the initial value problem. So we want to study the response of a system of some x of t starting at t equal to 0. That's why we're already integrating from this 0 minus. And yeah. So x of t should kind of starting at t equals 0. And so if you have a general signal and you might starting at t somewhere, then you want to do some changeable variable to shift the starting time to t equals 0, then you can apply your unilateral Laplace transform. Yeah, we'll see some example later. And anyway, that's back to another topic here. That is, so we cut off at t equal to 0 plus, 0 minus, and then this x of t is basically a right-sided function, right? Because all the left-sided, all the thing that go to t minus infinity doesn't matter. You can basically take that as 0. Then this is a right-sided function, so the ROC is always a right half plane. So like this, right half plane. Okay. So that's the first thing we know about the unilateral Laplace transform is we basically don't need to specify the ROC. Because you have a whole bunch of poles, then the ROC was always going to be the rightmost one. So that's nice. And yeah, from here you can also see that it's basically always causal. And that's also nice. And yeah, so when you do the inverse Laplace transform, then the unilateral Laplace transform is same as the bilateral Laplace transform. You just need to pick the ROC that's the rightmost side. Any question about this definition of unilateral Laplace transform? Not. Let's see some example. Okay. So if your x of t is 0 for all t less than 0, for example, this thing. So this polynomial times exponential decay times u of t, because u of t then obviously is cut off t equals 0. And then the unilateral Laplace transform and the bilateral Laplace transform should be equal, right? Because this integration is then as you extend it to minus infinity. Okay. Then yeah, then we've already seen this thing, and is a bilateral Laplace transform is going to be 1 over s plus a to the s power. And the ROC is the right side is is bigger than negative A. And that's nice confirms our intuition that the unilateral Laplace transform should take the rightmost ROC. Okay. And then we take another thing that's not so nice now. So basically we take our favorite exponential decay u and make a time shift. So now we have t plus 1 here and t plus 1 here. Okay. So this thing started at t equal to -1. Okay. And well, you can still do bilateral Laplace transform of this thing, and as we say, it's our favorite thing of 1 over x plus a, but there's a time shift. But so this time shift will give you e to the s here. And the ROC is the right side, is bigger than -a. But now you can do the unilateral Laplace transform of this thing. So you do this integral from 0. So this human of t plus 1 is not very useful. Anyway, you do the integral, then you see the form is e to the minus a 1 over s plus a. And ROC is the same, but now the equation is different. Okay. E to s here and e to the minus a here. So yeah. So you see that if your x of t has something at t less than 0, then when you do unilateral Laplace transform, you get cut off and you do different thing. So the unilateral Laplace transform is basically the bilateral Laplace transform of u of t, x of t times u of t, because u of t will cut off your x and t equals 0. Okay. Any question? Yeah, you do this u of t because you are integrating from t minus anyway. Although u of t is a little weird that really take singularity at t is equal to 0. So be cautious about doing this. Anyway, let's look at another example. Okay, so now we have our singularities at 0 here. Our x of t equals to delta of t, and this thing, what's it? Unidoublet. So 2u sub 1 here, and another u of t, e to the t u of t here. And yeah, and we want to do the unilateral Laplace transform on this thing. But so we have a singularity at t equals 0. But we say when we do the integral, we'll take whatever singularity at t equals 0. So when you do the integral, it's still same as the integral for the bilateral transform. Then you can just look up table of bilateral Laplace transform for all those things. And if you still remember, so delta should give you 1, and this u1 will give you 2s, because so as a reminder, so this u1 corresponding to differentiation, and differentiation will give you s. Okay, and this et ut is the standard form we have is 1 over s plus minus 1. And if you want to multiply everything together, you put on this, and ROC once again it should be the right-sided. So there's a pole at the 1, so you should pick ROC is bigger than 1. Real is bigger than 1. And now we have an example of inverse unilateral Laplace transform. And now we don't even write ROC, we just have your big X of s equal to 1 over s plus 1 times s plus 2. And obviously this thing has two poles, and s equal -1 and -2. And so now we don't need to specify ROC. So, and that's different from bilateral Laplace transform. So for bilateral Laplace transform, you have these two poles, and there are three possible ROC. It can be a right one, it can be a left one, it can be the middle one. But for the unilateral Laplace transform, we know the ROC must always pick the right side one. So yeah, so we know the ROC is the right side one. And then we do the inverse of this unilateral Laplace transform. So that's same as doing the inverse of the bilateral Laplace transform, knowing obviously this thing. And yeah, so that's what we've done multiple times. You do partial fraction expansion here, and you get s plus 1, s plus 2, minus s plus 2. Oh, I should put small s here. And yeah, and you get this e minus tu, e minus 2tu here. So x equal to this. And you should cut over the t bigger than t equal to 0 minus. Okay. And we write this because unilateral Laplace transform always only says about what the x of t is for t bigger than 0 minus. Okay. Just in time to have a break. So no question, then we have a break for now. Question? No. Okay. Let's have a 10-minute break. Oh, is OBS on? No. Let me.对，范围应该是第5章、第9章，然后，第10章，感觉有点难吧，可能会讲一点点这样子，但是可能考不太出来。对，应该主要是第5章、第9章。然后当然前面的东西还是要记得嘛，永远都会用到，你还是要记得 impulse response 之类的。但是我们主要会考第5章跟第9章。 Okay. Yeah, I think it's time to go back. So let's see more example of this unilateral Laplace transform. and we are okay. This example 9.38. So now we want to do another inverse unilateral Laplace transform, and now our Laplace transform is once again is rational function, so s squared minus 3 over s plus 2. And once again, we don't specify the RC because you know the RC is going to be bigger than -2. And so we do inverse of this thing just like we do the bilateral Laplace transform, we do partial fraction expansion. And because the order here is higher, the order of the numerator is higher than the order of the denominator, then you will get these extra terms. This extra parameter a plus bs, and so a plus bs plus c, and you can solve this. So here we are doing a stupid way: you multiply everything and try to solve the equation. But also you can just do long division to get this a plus bs, long division polynomials. But anyway, you do that, and you see your partial fraction expansion is -2 plus s plus 1 over s plus 2. And we know the RC is bigger than -2, then we do inverse transform of everything. So, and those two actually converge and you don't need RC. But you know, this is delta and this correspond to U1. Just like where we have U1 somewhere, yeah, just like here. So we know the Laplace transform of U1 is S. So inverse transform of S is U1. And this thing, you take the right RC, then C to the -2 times U of t. And yeah, this is true for t bigger than 0 minus. Any question? No. And yeah, then there are once again properties of unilateral Laplace transform, but we are going very fast, and we go straight into this table. It's because many of the unilateral Laplace transform properties basically same as the bilateral Laplace transform properties, and well, we'll just highlight some of the differences. So there's a difference here that when you do time scaling, you must take a bigger than 0. That's because, well, you want x of t to always start at t equals 0, and then if you do negative, then yeah, if you do negative, you split the negative part and the positive part, you basically get a totally different thing, because x over t less than 0, we think is 0. Yeah. And okay, the actual important thing is this. We are going to show a proof of this. So it's very different when you do differentiation on time domain. The unilateral Laplace transform, instead of just this x times big X, you also get this weird correction term of minus x on the 0 minus sign. Yeah. So yeah, so this is a very different part of the unilateral Laplace transform, and other things are basically similar. You have initial and final value theorem. And just for comparison, let's see the bilateral Laplace transform. So we have basically all the same properties. But as you see, for differentiation here, you just have x times big X. And also for bilateral Laplace transform, you have the time shifting property. But yeah, once again, you cannot really do time shifting for unilateral Laplace transform, because you do time shifting, you might shift out some x from t less than 0, now they become t bigger than 0, but you don't have the information about them before, then yeah, doesn't quite work with the cutoff at t0 minus. Okay. Yeah, so let's derive this differentiation property. And once again, the derivation is basically brute force calculation. But now we are using something that we don't quite use in this class, but also basic calculus, that is integration by part. So anyway, so on the differential property for unilateral Laplace transform, and we can just write down it. So we want the unilateral Laplace transform of dx dt, and that should be the integral z minus 0 minus to infinity dx dt, then times your usual e to the minus st dt. And yeah, we use the integration by part here. And so the thing we do here, we need to put things in slot. So what's u and v here? So u is e to the minus t, e to the minus t, and v is x of t. So because v equal to x of t, so let's see, let's try check. So we have u here, e to the minus t, and the dx dt times dt is like dx, and so that's dv. Okay, so everything check. So it's uv, and you need to write the boundary here, 0 and 0 minus. And then we have minus integration v du. So minus integration, let's see, so v is x, so integration of x is here, but we already do some calculation here, so du here, u is e to the minus st, so du should equal to minus st, and yeah, so minus s plus s. Things work out like this. And then you take the boundary, so at t goes to infinity, then obviously this goes to infinity, this goes to 0, but at 0 minus, and you get the extra term here. So at 0 minus, this exponential become 1, and you get x of 0 minus in the minus side. And the other part is just, this is just a unilateral Laplace transform of x of t, and then times s. So you see that from this boundary at 0 minus, you get this extra term here. Any question? Yeah. So that's that, and we'll be using this when we try to solve initial value problem, and you can do this for higher order thing, right? So this is the unilateral Laplace transform for dx dt, and if you apply this formula on dx dt, then you can get a unilateral Laplace transform of d square x dt square. So basically this thing times s, so it's this part, and times the x prime and minus the x prime and 0 minus, right? So yeah, so this is the unilateral Laplace transform for the second order derivative, and obviously you can get even higher derivative by just iterating this formula more and more, and you get higher and higher order s, and a whole bunch of these x or x prime and 0 minus. And I guess hope give you a little intuitive on why we need this minus x prime. Is you can take the think about some example of unilateral Laplace transform for two different functions. One is u of t, okay? And take u of t, you know the unilateral Laplace transform is one verse. We've been talking about this a few times. And now you take the derivative of this thing, then you get the delta of t. And then the unilateral Laplace transform, well, if you use this formula, then that's s times 1 versus 1, then minus. So it's 0 minus, this u of t is 0, so minus 0, so that's 1. And that also confirms with what we think. We think delta of t will unilateral Laplace transform to 1. But Now if you do some time shift, so instead of doing u of t, you take u of t plus 1. So you have something that, so it's a function that goes like this. And so this jump happen at -1, and those parts should be cut off. But point is now the 0 minus here is a +1. But anyway, so if you have u of t plus 1, and you do unilateral Laplace transform, then the extra part basically get cut off, and so you get the same unilateral Laplace transform of one ways. But now if you take a derivative of this thing, now it's a spike at -1. And because of that spike, you don't see a unilateral Laplace transform. So the unilateral Laplace transform of this delta t plus 1 should be equal to 0. And that also check with its formula, because s, once again, s times x over s is 1 here, but you minus x of 0 minus. Now the 0 minus is 1, so that's 1 minus 1 equals 0. Okay, so yeah, so this formula makes sense, because you want to kind of like, because you want to check the value at the x0 minus to see whether there's a jump at 0. Okay, yeah, that's hopefully give you some intuition, but if not, then the bottom line is you need to remember those two formula, or remember how to derive them, because they are useful. Question? If not, okay, then let's really try to remember this, and let's see other property. And well, we have a convolution property for unilateral Laplace transform. Oh, we didn't talk about it, but they are also a little different. Okay, do we have them? Yeah. So it looks the same here, but we need different assumption here. So we need to assume that x of t and x1 of t and x of t are all 0 when t less than 0. Basically because the unilateral Laplace transform don't see the t less than 0 part, but the convolution see them. So if you have something at t less than 0, that can mess up this relation. So you want your x1 and x2 both start at t equals 0. Okay. And but if this is satisfied, then we have our usual convolution relationship. So x1 coupled with x2 will give you the unilateral Laplace transform, give you big x1, big x2. Okay. And then we can use this to derive some other property. So for example, so you start with your nice x that starts at t equals to 0. Then then you can derive the integration formula, because this integration is same as convolution with u. And convolution with u will have this integration cut off at 0. And then you do unilateral Laplace transform of this thing. Then that's a multiplication of big X and big U, and big U is 1 raised, so 1 raised big X. So you can derive the unilateral Laplace transform of integration. And then this is 1 raised times X, as we expected. Okay, question? So yeah, it's a little symmetric, but that's what happened. So differentiation, you get this boundary return correction, but the integration is still the same 1 raised. Okay. And also for the integration, we need to start at t minus. That's just that. Whereas t equal to 0 minus, but whereas for bilateral, you integration start from minus infinity. So that's also different. Okay. But so finally we can solve our LTI system. And we start with this kind of like old example. So we solve a causal relativity system by this different constant differential equation, constant coefficient differential equation. So it's 1, 3, 2, and x, and it's causal LTI. So it's basically we have the condition that have initial rest, and we do a little more restriction that we want x starting at t equal to 0. And so if we have x starting at t equal to 0, then the unilateral Laplace transform basically sends us the so the unilateral Laplace transform will send us the bilateral Laplace transform, right? Because of this and the initial rate. So x of t and y of t are all starting at t equal to 0. And so I guess we should say the unilateral system function will equal to the bilateral system function, and we know how to calculate the bilateral system function. If it's 1 and over is 1, 3, 2. Okay? And so that's the unilateral Laplace transform of the system. And then we can, where are we? Yeah. Then we can solve things. So now if we have some x of t equals this, and then together with this initial rate condition, then we can solve output y. And by doing this, so we just talk about convolution property. And now this is a causal LTI system. And okay, let's see a little more careful that everything check. So we have a causal LTI system. So y should equal to x of t convolute with h of t. And we know, okay, we didn't quite say, but yeah, we can assume that h of t also start at t equals 0, and we have x of t start at t equals 0. So this is satisfied, and then this equation is satisfied. So big Y should equal to big H times big X for the unilateral things. Okay, and yeah. And well, we can do the unilateral Laplace transform of this thing, basically saying as the bilateral one is a one where, so it's u, so it's one race. So you multiply this with one race, you get this. And once again, you do partial fraction expansion. And now it's unilateral. You know you need to take a right-most ROC. So you can do the inverse, so it's become u and e minus tu and e minus 2u. Okay, so that's yeah, and now using things check, right? You take a unilateral, taking the right-most ROC, and that's corresponding to your causal system. So yeah, so this is basically the same as what we do with Fourier transform on chapter 4, but a little different notation. Okay, so this is being what we know how to do to solve differential equation. But now there's something we didn't know how to do with solving a differential equation with initial condition. Okay, so now we want to solve this still the same differential equation is 1, 3, 2. And also the same input x of t equal to a u of t, but we want to solve this with initial condition, so not the initial rates anymore. So we want y the 0 minus to be beta, and y prime is 0 minus to be gamma. So let's sketch. Yeah, so you want your system to start in the response to always start with some value beta here and with some slope gamma here. Okay. And yeah, so this is where the differential property works. And we do the unilateral Laplace transform on this equation. So think about this on both sides. And well, you do x of t, and this is alpha u of t, then unilateral Laplace transform, you get alpha over s, that's the same. And so y become 2y become 2 big Y, but the dy dt now you really need to use a differential property, right? So dy dt will write big X, but so dy dt should become S times big Y, and minus minus Y at 0 minus, right? And but now we have Y at 0 minus coming from this initial condition, so that's beta. So you know the dy dt, when you do unilateral Laplace transform, it should become sy minus beta. And then you times 3, and so you get 3 here, 3 here. And similarly, this d squared y dt squared, we use this second order differential property that we also had before. So it should become s squared big Y minus s y is 0 minus y prime is 0 minus. And once again, this y is 0 minus is beta, and y prime is 0 minus is gamma. So this becomes s squared y minus beta s minus gamma. So we now have this new equation between, I guess this new equation on y. Okay, this is incorporating the initial condition, and we got this. And yeah, we can move things around and make things nicer. So then solve for y, and it's equal to this return. So a term that proportional to beta here, a term proportional to gamma here, and term proportional to alpha here. Any question on how we get this? So this is how we solve initial value problem with unilateral Laplace transform. So you still do unilateral Laplace transform of this question, but now you get a whole bunch of terms that depend on initial condition, beta and gamma. See this term here and this term here, and well, they are still rational. And well, before we solve this, we say something. So first, compare to what we just did here, right? We just did here, we see that y is equal to alpha over s plus 1, s plus 2, and you see it's same as this term here. That's what happens when we have a causal LTI system. We say a causal LTI system with initial rest. Okay, and so you see that this term will corresponding to the initial rest term. And that makes sense, right? Because initial rest means that, if you remember the initial rest condition we defined, is that you take the y prime equal to 0 at t less than 0. So yeah, so if beta and gamma equal to 0, then that's the initial rest condition. Then these two terms disappear, and you have a causal LTI system, and it will satisfy this, and yeah, you have h of alpha equal to s plus 1 s over plus 2. Okay, and as we said, that's the causal LTI system that corresponding to condition of initial rest. And we have some name here. Then this initial rest condition response is called the zero state response. Okay, it's called zero state because that's when the initial state is 0. Okay, and then there are other things that we also have those two other terms that only depend on the initial condition, basically, because you see these two other terms, they exist even if alpha equals to 0. So you put alpha equal to 0, the XOT is equal to 0, but I still have this y of s. So they totally come from this initial condition here. They doesn't depend on XOT at all. XOT equals 0, they are still here. Okay, and because that those two terms are called zero input response. Okay, so we have a zero state response and zero input response. And obviously I call zero input response because that's the response you get even when the input is 0. And yeah, and interesting about this system from differential equation is that your response is the sum of the zero input response plus the zero state response. Yeah. Yeah. And yeah, that's what I say. So the overall response is the sum of zero input response and the zero state response. Oh, and the other thing we forgot to say. And the zero input response is going to be the linear function on the initial condition. So basically, the linear function on beta and the gamma. You see, it's linear in beta here and linear in gamma here. So if you take beta to 2 beta and gamma to 2 gamma, then this zero state response, the zero input response will get double. Something like that. It's linear. And so, well, this is an example, but you can see that this is general for every differential equation. Any initial value, initial value problem with initial condition will have this zero input response and zero state response, and your output is a linear combination of them, and and yeah, they are all linear. And each individual term is either linear in the initial conditions or linear in the input, because it's a linear system. Okay. Then let's finish solving the question. So if y equal to this thing, so if we plug in some, well, now it's basically this thing here. If we plug in some alpha, beta, gamma, then we can solve for y. Well, if we not, we can also solve, but it's only going to be a little annoying. So let's say alpha, beta, gamma equal to some value. Then we can do our favorite partial fraction expansion. And yeah, because you can see it's some rational, and you can do partial fraction expansion of each one separately. And we skip all that and give you the result here. And well, we can check that it makes sense, because it has turned that proportional to this s and proportional to s plus 1, because everything is part of s plus 1, and proportional to s plus 2, 1 over s plus 2. Okay. So we skip the calculation, and you get a partial fraction expansion here. And then you just do inverse unilateral Laplace transform. And yeah, that's quite easy. You get UT and the exponential on every of them. So that's your y of t here. And yeah, I think that's for chapter 9. So any question? 抱歉，同学问题我没看到。如果使用双边跟单边Laplace transform，OK，所以你应该有回答到你的问题。所以这样有回答问题吗？因为双边的没办法解 initial value problem。对，因为单边的才能看到这个 initial value problem， 这个zero input response form。对，做完加入。Okay, yeah. So yeah, this is what we keep talking about. Where we want Laplace transform, and in particular this unilateral Laplace transform, is because we want to solve initial value problem. And yeah, from this you can see the terms are proportional to your initial value here. And it's quite cool. So yeah, so this is not a total story. And I guess also a thing I want to emphasize is that if you look at this, so this beta and gamma term, those zero input response. If you are looking towards the zero input response, and so I should say, okay, I need to say this carefully. And what I want to say is you fix some beta and gamma not equal to 0, so you have some fixed initial value, but now initial rate is initial something, then your system is not going to be LTI. Okay? Because basically because the system is not linear in alpha anymore. Because you have this beta gamma term here, so if you multiply your input by another factor, so basically multiply alpha by another factor, then your y is not going to get multiplied by another factor because you have beta gamma term here. So yeah, so be careful if your system solve a differential equation but with a non-zero initial condition, then that's not LTI. But if both zero, then that's causal LTI. I think we're doing unilateral Laplace transform, right? So whatever we do here, our system, so this is another LTI system, but it's still a system and it's still the causal system. But it is LTI only if beta and gamma equal to 0. That's what happened, yeah. That's what happened on the zero state response. But if you have this zero input response, then it's not LTI in this XY sense, but maybe you can do something weird like incorporating initial condition as the input, but that's not what we're doing, so I just say it's not a linear system anymore. Okay. And yeah, and I guess we keep saying this because we want to fix the field gable. We have been deriving this and or the relation, all things correct, so why doesn't this work on initial value condition? And that's because for initial value condition it's not LTI system, so this doesn't quite work. Okay. Yeah, and you can think about detail more. Oh, and we got about 20 minutes to take about chapter 10. Okay, that's actually should be enough to talk very short about our chapter 10. Let's go. That's 4th slide for the chapter 10. Let's see if I can do this. So PowerPoint here, and I need to change. Oh. Okay, OBS is pretty smart. Okay, chapter 10 in 4th slide. And actually we can make test function on here, but I can give you a general idea about this Z transform. So this transform is it's basically a Laplace transform for discrete system. And yeah, for discrete time system, once again, we want the Laplace transform to be the function of the eigenvalue of all those eigenfunctions, right? So we know the eigenfunction when you have a discrete system is z to the n, and so y of n will equal to h of z and z to the n. And so at chapter 5 we have z equal to e to the j omega, but now we have arbitrary z. Okay, so z is not e to the j omega anymore. And when that happens, then we have the z transform. And yeah, and we can write h of z as this summation. So we had this solution before. So h of z will be summation small h of n and z to the minus n. Okay? And if we compare this to the continuous sum case, the continuous sum case big X is so summation become integral is similar, and x of t and h of n similar. But so we have z to the minus n here, but we have e to the st here. So you compare those two things, you see that z is basically e to the s. Okay, and yeah, that's like basically the difference between Z transform and the Laplace transform is instead of plotting on S, you will plotting on Z, and Z will be e to the S, and it will be a little different. And so this slide will have the formal definition. So basically the same thing, you change h to x. So small x, small h, big X, big H. Okay. So the definition of the Z transform, and obviously you can have a transform pair back and forth. So X over N and H of Z. And it's a little different, but this is discrete, but it's still continuous. Okay. And that's just what happened. And okay, so the important thing here is, well, we want to draw on Z-plane and we want to see our C and stuff. So the first thing happen is that the things, maybe it's easier to see this. So basically the LCs are going to be donuts, or what should I say, they are going to be separated by circles. And that's because, so we have a comparison here. So for the Laplace transform, the ROC are strips, right? So you draw an S-plane and they are posed somewhere, and the ROC will be like these vertical strips, and they are separated by those poles, and maybe extend to right infinity or something. And then now you draw on Z-plane, and then remember Z equal to e to the S, right? And now you think about this in polar coordinate. And Z equal to e to the S, and if you think Z equal to some R equal to j omega, and so you write Z in polar coordinate, you can write AC in the orthogonal coordinates, so sigma plus j omega. Then R should equal to e to the sigma, and you have this omega also equal to this omega here. But the difference thing here is, so you know that for discrete signal, you have this 2 pi period in omega, right? So yeah, this is something we keep stressing. So if you have a discrete signal, then you do Fourier transform, then you have this 2 pi 2 pi period in your frequency domain always. And this is exactly captured in this Z-plane, because you want e to the j omega plus 2 pi n equal to e to the j omega n. So omega gets 2 pi more, and yeah, your whatever function, your Z-plane or S-plane or omega axis representation should be the same, because the n is an integer. And that means that if you draw on this S-plane, then this is 2 pi period in the imaginary direction, right? But now you draw this Z-plane, so this imaginary direction, if you do this exponentiate, and then you see that you go this direction, then you see the angle here, right? So if you go from 0 to infinity, then you are just looping circles on the Z-plane, because that's no, instead of the imaginary axis, it's actually the angle of your Z. It is e to j omega here, and you automatically get this 2 pi period here. Okay, so if you are thinking about Fourier transform and you look on this j omega axis, then you see that you have some period 2 pi here. Here is automatically, you see everything is periodic with period 2 pi, because you get a 2 pi cycle back, then you are just going back to the same location, and then that has the same value on this Z-plane, and that's nice. And let's go back to this R axis. So now, and yeah, so you see that when you go in y direction, go in this j omega direction in the S-plane, then you are actually walking in circle in this Z-plane. And now if you go left and right, so in this real direction of S-plane, you will go in radial direction of this Z-plane. So if you go to negative infinity of sigma, that means you are approaching this 0 point, this origin here on your z-plane. And if sigma go to plus infinity, then that's also you are going to alter in the infinity circle on the z-plane. And okay, and now a few things. And yeah, so here we have some picture for the angle here, and then yeah, we can basically do correspondence of everything to the z-plane. So one thing we say is the geometric axis corresponding to doing Fourier transform, right? And then your geometric axis is straight line here. You take z to equal to e to the s. Then you see it's actually a unit circle on the plane. Okay. So the unit circle will corresponding to doing Fourier transform for your discrete signal. And then the shape of the ROC, as you can see here, this is one example, but you can probably guess another. So the shape of ROC instead of strips is going to be rings. Right? So you are still going to get a whole bunch of poles everywhere, and your ROC will be restricted by the poles. So your ROC is going to be between poles, but there will be rings. So let me try to draw. So maybe if you have a pole here, then this pole will give you another circle, and your ROC maybe the inner ring or the outer ring like this. So here we have the ROC being outer ring, and maybe your ROC is the most inner ring, something like this. Okay, so there are many possibilities of ROC, and they are all going to be rings. And so that's actually not a lot different, right? So kind of just changing, kind of just changing notation. You are doing this exponential, so ROC and poles and everything will come in circles here. And I guess that's basically it. Or something a little different is that now this middle point here corresponding to you take sigma to negative infinity, and we usually on the S plane we don't look at this negative infinity too much because there's an infinity, but here is in the middle of everything, and yeah, and so you can have 0 and poles here, and it's a little weird. And yeah, and you need to think about its property. Yeah. Okay, we have 5 minutes left. I don't think we can talk in too much detail, but so I guess I'll talk a little more. But so basically, every property of the analysis on S plane translate into the analysis on Z plane. So for example, if you want your system to stable, then your ROC need to include this unit circle because you need to include your Fourier transform. And if you want to be causal, on the S plane is you need to take the rightmost, and on Z plane you need to take the almost. And obviously you can do the posterior analysis here too. And I did have that. And yeah, and when you do inverse Laplace transform, you also do partial fraction expansion, although the function is a little different. I should cut that. Any questions so far? Yeah, so we also have the right-sided function, left-sided function will be in your order. Okay, we have 5 minutes. Let's try to pull really quick to see I can find the partial fraction expansion here. Real Chapter 10. Okay, yeah. I think it's this. Yeah. In Chapter 10. So it's very similar to Chapter 9. And so the thing we like most is still this exponential decay function. Okay. And and we have regional convergence. And well, the regional convergence is going to be supervised on absolute value of A. Anyway, so you do this thing and it will become, so now it's a little different form. The form will be z over z minus a, or 1 over 1 minus a z minus 1. Okay. So yeah. So this is the basic pair we'll use all the time when you do discrete time. If you have this exponential signal, then you get z transform and it becomes this z over z minus a. And this thing obviously has a pole at a, and you need to take an ROC that the absolute value of z either bigger or less than something. And okay, so that's that. And also we have the corresponding part where the signal is the exponential decay to negative time, and we'll get the Laplace transform, but with a different part of the RC. Okay, so this thing. And now we still have time. We are so fast. Do you guys have any questions? Or you are just zooming out because I say I'm not going to take an exam here. Anyway, yeah, it's very similar, and I think we do similar things, right? So, we have an example of partial fraction expansion. The regional convergence is similar. Let's see if we go to inverse, we have inverse Laplace transform, inverse z transform over here. Okay, so you have pole zero plot. And you can have many other pole at 0, it's a little weird. And a different signal. We have signal and integer. Once again, you want ROC to overlap, otherwise you are bad. Okay, and inverse Laplace transform. Okay, and if you want to do contour integral, wait. And if you want to do contour integral, then I think you want to integrating over a circle, because yeah, instead of integrating a straight line, you want to integrating a circle inside ROC. Okay, circle with some radius that's inside your ROC. So that's that, and we don't really know how to do it. And the other thing is you can do partial fraction expansion. Once again, you get this thing and think about exponential signals. Okay, so this is exponential signal. Okay, I'll basically finish chapter 10 in 15 minutes. Okay, well, maybe not too much exam here. Yeah, I think we're out of time. So any more questions, or there are more strips? Okay, a little something else. Yeah, and we have a method 3, but we don't have time to cover. Yeah, so if you don't have question, we'll have final review on Tuesday, and we'll take your final. Okay. 作业是第10章的作业，应该会 po 吧？还没 po 吗？子静可以 po 一下，我们会直接把作业跟解答 po 上来。对，好，所以大概这样。对啊，因为抱歉第10章没有教完。 但是我时间比较紧迫。通讯原理用到我没教的，可能会有一些吧，好像有一些 sample 之类的。第十章，第十章应该不会考很多吧，因为我们教的实在太短了，只教了15分钟而已。可能会考的话，应该也会考一些比较基本的吧，对啊，因为毕竟 sample 什么都没有看嘛，我们只是就是这样子大概的看一下。虽然说第十章跟第9章都很像啊，所以可能也没有太多好考的。对，好，其他问题吗？没有的话就下礼拜见。哦，在温室考试时间就是上课时间啊，下礼拜5，然后一样上课时间。会跟上次一样多30分钟这样子，所以应该是下礼拜5的3点半到6点这样。会用到我没教的，好像是会用到我没教的吧？有一些有趣的什么 sampling 之类的事情，sampling attenuation 之类的。Laplace Transform 表格，对啊，应该会提供，会跟期中考的时候一样提供。但是自己的小抄作业这样子，虽然说不太能确认，但是希望同学有，希望同学有自行符合规定。准。OK，如果没事的话，那我们就下课。